Let n be a positive integer, and let a1, a2, all the way to an be non-negative real numbers. Show that the sum on the left-hand side is less than or equal to 1. Moreover, determine all of the cases of equality. So this sum looks really messy at first, but we have all of these 1 plus a1 and 1 plus a2 and all of these things, so we might want to consider the problem in terms of those. The first thing we start off with is a 1 over 1 plus a1. We can't really do anything with that, so we just leave that as is. Now we have the next term, a1 over 1 plus a1 times 1 plus a2. Here we have a1 over 1 plus a1 times 1 over 1 plus a2. Here we're separating out the a1s and a2s just to make things look a bit nicer. And we don't want things to mix up. So we have a1 over 1 plus a2 times 1, this should be a1, 1 over 1 plus a2. And we have similar terms for the rest of them. So we have a1 over 1 plus a1 times a2 this time over 1 plus a2, and then times 1 over 1 plus a3. And as you'd expect, this pattern continues all the way until we get to a1 over 1 plus a1 times a2 over 1 plus a2 times all the way to an minus 1 over 1 plus an minus 1 times 1 over 1 plus a sub n. And we want to show that this is less than or equal to 1. And now we immediately notice that the sum of these two fractions here is equal to 1. So a1 over 1 plus a1 is equal to 1 minus 1 over 1 plus a1. And this holds for any index I, so we can instead do that. And this really motivates us to focus on the fraction 1 over 1 plus ai, and motivates us to substitute x sub I is equal to 1 over 1 plus ai. Now let's examine the properties of the xi. First of all, the ai are non-negative as given in the problem statement here. So that means that x sub I is less than or equal to 1, because as a gets larger, this is only going to decrease. And since the reciprocal of a fraction can never be 0, this is also less than 0. So now we just eliminated all the a's from the problem, and we've rephrased the problem to 0 is less than xi is less than or equal to 1 for all I between 1 and n. And now we'd like to show that x1 plus 1 minus x1 times x2 plus 1 minus x2, 1 times 1 minus x2, x3, and we continue all the way to plus 1 minus x1, 1 minus x2, all the way to 1 minus xn minus 1 times xn. And we want to show this is less than or equal to 1. For 0 is less than xi is less than or equal to 1. And so now that we have these values of xi less than or equal to 1 and greater than 0, and now we have 1 minus x1 in the equation and we continue having them, this motivates us to consider using probability. So in particular, we can try looking at this in terms of like n coins. We have n coins here. So this is coin 1, coin 2, coin 3, all the way to coin n. Then the coin 1, suppose it has a chance x1 of being heads. And coin 2 has chance x2 of being heads. And then x3 of being heads, and so on all the way to xn of being heads. And this process here is just flipping the coins one by one in this order until we get heads. And this is the probability that we get heads. This is because, so we start with the first coin, we flip it. If it gets heads, we're done. This is probability x1. Otherwise, in the case that it doesn't get heads, it's 1 minus x1. And then we have x2 if that becomes heads. And then the probability that these first two are tails, and this is heads, is 1 minus x1 times 1 minus x2, x3. And you can expect that this process continues all the way to the first n minus 1 are tails, and the last one is heads. So that gives the last case. All the way to 1 minus x n minus 1, and then xn. This is the probability of seeing heads. And obviously, because probabilities are always less than or equal to 1, this is less than or equal to 1. And we have just solved the problem using probability. Now let's determine when equality holds. So we're flipping a bunch of heads here, and if all of these probabilities are always less than 1, there's always a small chance that we roll all tails. And we don't want that to happen. So the only way we cannot have all tails is if one of the coins is rigged to always come up heads. This means that for some I, we have 1 over 1 plus xi is equal to 1. And then solving, and this would be ai. And solving for ai, we end up getting ai is equal to 0. So therefore, equality holds if and only if at least one of the ai are equal to 0. And there we have it. We solved this seemingly hard algebra problem using combinatorics and probability. And we used that to also determine the equality case. So thank you so much for watching this video. Please subscribe if you'd like to see more.